So we're at the Sanford Natural Area. So this is a location on campus in Michigan State University campus, and it's an area where we've gone from an urban environment to a somewhat more natural environment. So the Sanford Natural Area is a very large riparian buffer zone. This is a place that's very vegetated. There's lots of trees. During the summer, there's more understory, and we're just going to take a look at how the river looks in a place where more restoration's happening along the banks of the river versus what it looked like when we're in the more urbanized areas. One of the things that is kind of interesting about this area is, as you look behind me here, you can see a lot of the forested region that makes up the riparian buffer zone that helps protect the Red Cedar River from stormwater runoff. But if we turn around and look at the opposite side of the river, you'll notice that there's some pretty extensive development. This is an apartment village that's across campus, and if you look behind me here, you can see this very large storm drain. So during peak rainfall events and the storm systems are full, they will empty out into the river right here, all right, just on the other side of the natural area. So I just collected a water sample from here. Again, we're still in the Sanford Natural Area. We still have the development on the opposite side of the river. So this sample is going to represent something that is kind of a hybrid between a natural area and an urbanized area.
So here we are in Alaska. And just to give you some perspective. And then we have actually several glaciers that are entering into the bay here. This is the Columbia Glacier. And this blue line here is representing the current end or terminus of the glacier. So where the glacier terminates is called the glacial terminus. And the most recent one that we have in these satellite images is from 2017. So I just drew a line to show where the terminus ends. So basically what I did was I went to this back in time button at the top, and I can actually look at previous images of the glaciers. This is back in 2015, and I just created a path where I traced the end of the glacier. 2012. So this is 2007. Right, so that's how I got this terminus here. So in the assignment, you're being asked to look at the time that's elapsed. So for example, from 2007 to 2012, there's been 5 years. Right, so you'd put 5 years in here. And then the distance between the two terminus between 7 and 12 in kilometers. So here's the 2007 terminus and the 2012 terminus. And we're going to use our measure tool, and we want our distance in kilometers. So we'll use the drop down arrow to change that. And so now I'm just measuring the distance. And so you'll notice that depending on where you're measuring, you're going to get a different measurement. So there's a couple ways that you can do this. We want the average distance. So you could either try to eyeball what you think is about a good middle. Right, so what's not the shortest and not the longest, but looks to appear to be about the average distance. Or you could measure a bunch of times across this and then take the average of those measurements. 2.7 in here because it was 2.66, so I'll round up. And so my rate of glacial retreat is just the distance that's changed over the time. right? So 2.7 divided by 5, which means I get a rate of ice loss of 0.54 kilometers per year.
So I just happen to have these 3 different materials laying around the house that I know all float in water. So I have a block of foam, I have a block of wood, and I have this block of very high density plastic. I believe it's called starboard. All right, so in order to do this experiment, I need to know the density of each of these materials. And I know that the density of water is 1 gram per cubic centimeter. So I can weigh each of these in grams and then record it on my little data sheet. And then I can get its volume in cubic centimeters by just measuring the length of the object, the width of it, and then its height in centimeters. Right, so then later we'll multiply those to get volume, and then we'll divide mass divided by volume to get density. The other thing we need to know is how much did these float above the water line. So the idea is that lower density things are going to sit higher above the water line, and higher density things, especially when they're close to the equal density of water, they're going to like sit below the water line, barely floating. So here's the foam block. Here's the wood block. And then here's my piece of plastic, which is pretty close to the density of water. This foam block is pretty much all above water except for a tiny little bit. This wood block is sitting almost 50-50 at the water line. And this plastic block is almost entirely submerged, and just a very tiny little bit is sticking above the water line.
So we're going to look at a couple of demonstrations where I recreated these 2 environments to show you the displacement of these little paper foot walls and hanging walls that I created. Now let's look at ductile deformation. So when we compress layers of rock in a ductile regime, then what we start to create is a sort of rippling of the rock layers. So I'm going to show you the 2 main types of folds that we can get as we compress layers of rock, known as an anticline and a syncline.